Hello everyone, thank you Ramji and the organization for inviting me. So I will discuss this joint work with Chun Lam Cham and Nicolas Macri, who are my colleagues in EPFL, about the canonical stochastic block model. I will show you how to obtain a simple formula for the mutual information of this model directly, and I will precise what do I mean by directly. So this work really started as an exercise, because the results I will present are not new, the theorem is not new. What is new is more the methodology, so we thought it's interesting. So the model we consider is the canonical stochastic block model, so consider n nodes, or spins, I'm a physicist, I like to call things spins, xi's, which are drawn according to this prior distribution, so there are ID variables with the probability R, they are +1, so blue if you want, they are in this group. With probability 1 minus R, they are red, okay, a -1. So you can have two different sizes, okay? Then I require that the model is so-called balanced and dense. So what does it mean? Balanced means that whatever the community you belong to, your average degree is the same, okay? You cannot extract any information from the degrees of the nodes, okay? Moreover, I require that this expected degree goes to infinity, and this is controlled by this sequence, P here. This doesn't have to go linearly to infinity in n, but it has to grow, okay? So this is what I call dense. In addition, so once you have planted this partition, you have created these two communities, the way you create the edges, the way you create the adjacency matrix is through this probability distribution. So you put an edge between two nodes according to this law, and you see that this delta n controls the fact that you are or assortative when it is positive, which means that you have a highest probability to connect to someone of the same color within the same group as yours. This assortative case means that you connect with highest probability to spins which are in the opposite community. Then let me define this so-called signal-to-noise ratio, which is this quantity, and I require that this quantity remains constant when I will let n, which is the number of nodes here, grow to infinity at some point during the analysis. So you see that it can really be interpreted as a signal-to-noise ratio because you see this delta square here, and indeed this delta controls the strength of the signal, which means you see that here the information contained about this planted partition is really related to the strength of this delta. If delta is 0, you have a graph which does not contain any information about the communities, okay? So you can keep this working example in mind. Delta n goes to 0 as 1 over n to the 2/3, and it's much lower than this Pn, which goes like this. And the fact that this signal strength is much lower than this quantity that you can think as a measure of noise is coming from this requirement. And we will see that this quantity will naturally appear in the analysis. Okay, so what's the inference problem? So now you have created this graph. So I have created this graph, and I will not give it to you. Instead, I will give you this graph, which is the same, instead that I remove the colors, you don't know the labels, and I reshuffle the graph such that you don't see easily this structure, okay? And I ask you, given this graph, can you recover the two partitions, okay? Another way to see the problem is that I give you the adjacency matrix, but with the rows and the columns that have been randomly permuted. Can you recover this permutation where you clearly see appearing the community structure, okay? So there are many people that have worked on this problem. It started with this paper by Docel et al., so where they conjectured this phase diagram, so this behavior based on statistical physics computation, and then a bunch of people work on that and made this picture rigorous. So what is this picture? On the left side, I plot the signal-to-noise ratio, which is a measure of how complicated is the problem, how difficult it is to reconstruct these communities. And here you have the group asymmetry, okay? So here, above the blue line, you are in the so-called easy phase. Easy, what does it mean? It means that there is an algorithm which is polynomial in time and which is provably optimal. So it will reconstruct these communities the best the best you can do, okay? And this algorithm is actually a version of belief propagation, and it is related to the so-called non-backtracking operator. Yes.
Exact recovery?
No, not exact recovery. It means that you can say something here which is non-trivial, better than random guessing. Yes, yes. In the impossible regime, it means that you cannot do anything better than random guessing, and this independently of any algorithm you use, okay? So this is really an information theoretic result. And here you have a very nice phase, which we call hard. Hard, why? Because here, information theoretically, there is information in this graph that would allow you, if you would have access to the optimal algorithm, to reconstruct non-trivially these communities, but we don't know any algorithm able to do so, okay? So these kind of pictures with an easy, hard, and impossible phase are actually very generic and appears in very many high-dimensional inference and learning problems, actually. So this picture has been taken in the paper by Miolan and Lelarge. All right, so the theorem in this work, which is not new, is the following. So let me define this simple function that depends on Q and the signal-to-noise ratio in the problem. Like this, okay, so Q is just a scalar. P of R, which appears here, is the prior with which we created the communities, okay? This X and this Z are scalar variable. Z is a standard Gaussian. And the theorem tells you that the asymptotic value of the mutual information between the adjacency matrix and the planted partition is given in the limit by this simple scalar optimization problem, okay? So you convert the problem of computing this very nasty object into this very simple scalar optimization problem. By the so-called high MMSE relation, as a corollary, you can get the value of the minimum mean square error. So if you derive this expression with respect to lambda, you obtain the value of this MMSE here, where X hat is the optimal estimator given the adjacency graph. And it is given by this simple formula where Q star is defined as the argmin of this function that I will call the potential. And actually, this Q star can be interpreted, actually it can be proven, that it is equal to the overlap, which means the scalar product between the optimal estimator, so the minimum mean square estimator, and the true partition. Okay? All right, so this result has been obtained heuristically. Heuristic does not mean approximately. It's an exact computation. It's just non-rigorous, thanks to the so-called replica method from statistical physics by Le Sueur, Zakalans, de Borova. And this result has been first proven rigorously. Actually, the first one was by Corrada and Macri, but they didn't realize that the model they were looking at was actually the SBM, but they were working on something else, but it's actually equivalent. And then by Deshpande, Montanari, and Abe, who proved this formula in the case where R is 1/2, which means that the two groups are of the same size, and you are in this regime here. And actually, this analysis relies strongly on the fact that you don't have discontinuity, a discontinuous phase transition. What does it mean? It means that you don't have a gap like here between computational to statistical. So we call that a computational to statistical gap. When you have one, it makes the analysis more complicated. Here you don't have one, and so they managed to obtain this proof. Then what we did later, including with Nicolas Macri and the physicist from Paris and Mohamed Zia, is to prove this general picture, so for any R, and this has been followed by work by Miolan and Lelarge. So if you want to know about the history of this very nice problem, I recommend you this review paper by Emmanuel Abbé. All right, so what people were doing to obtain results on this stochastic block model. So what they were doing is not to directly study this model, but instead to first map it onto another problem, which is much easier to study a priori, which is the so-called rank 1 matrix factorization problem that you can see as a simple probabilistic version of principal component analysis. So the problem is the following. You have a vector X that you multiply by its self-transpose. You add Gaussian noise, and you obtain a matrix Y. The inference problem is, given this matrix, can you recover its low-rank representation, which means this vector X, okay? And what you can prove is actually that the mutual information for this problem between this observation matrix and the vector is exactly equal to the one of the stochastic block model. Okay? And people use this link to prove results on the stochastic block model, because it's actually easier to work with this model because you have Gaussian noise, and this helps a lot. Okay? So let me try to convince you heuristically that this is the case. So consider the edge variables, so these Bernoulli variables with this given mean and variance. Okay, recall that this noise term, if you want, is much higher than the signal term, which is here. And so at first approximation, you can say that the variance of these variables is actually approximately equal just to the pure noise term. Okay? You just cancel this term. Then if you try to define a random variable which is approximately equal in distribution to these Bernoulli variables, you try to match only the first and second moments, what you obtain is a Gaussian variable, which looks like this. This is the mean, and the variance is Pn, and here you have a standard Gaussian. Okay? So this is an approximate equality. And then I just put that on the other side, and I rescale by this square root here, and I define this matrix Yij, which looks like this. And here exactly appears my definition of the signal-to-noise ratio. Okay? This is the link between this strange quantity that appears in the problem here and these quantities that define the stochastic block model. And you see that here I exactly recovered this model, which is here. Okay, so this argument can be made rigorous thanks to the so-called Lindeberg principle, and this is what have done Deshpande, Montanari, and Abe when they studied this model. All right, so what we did is we asked ourselves the following question. Can we do the proof, but without going through this mapping? Okay, can we directly tackle the stochastic block model? So the difficulty is that you don't work with a Gaussian model and Gaussian noise, which we like because computations are easier. Instead, we work with Bernoulli variables, and this complicates the analysis. Okay, but actually you can. So what we used is the so-called adaptive interpolation method, which is a technique that I've developed together with Nicolas Macri. So the goal is to prove this identity. So I recall here the expression of this potential. Okay, and if you look carefully this term, which is here, actually you realize that this is nothing else than the mutual information of a scalar Gaussian channel. Okay? So here x is a scalar variable. So here the expectation is over this big x and over this big z, which is also scalar. And this is nothing else than this object, okay, where q is a free parameter. So this is the mutual information, what I call an effective or scalar or decoupled Gaussian channel. And this kind of term actually appears almost universally in all these high-dimensional inference problems which have an underlying dense graphical structure, which is the case here in the SBM. Okay? So this is the kind of models that we like to call mean field in physics. Okay? All right, so now you have realized that you have hidden in the formula a Gaussian model. What we do is to define a kind of extended model, which we call the interpolating model, which is parameterized by a parameter t that we call time that belongs to 0, 1. And what we say is that instead of just having access to this adjacency matrix, we say that instead we have access to two kinds of observations, okay? We have this Bernoulli variable, so this adjacency matrix that now depends on time, and you see that I rescaled the signal term by the square root 1 minus t. But in addition, to compensate, if you want, I add Gaussian observations related to my partition, okay? But you see that these Gaussian observations, they are uncoupled, okay? Here you have just the index I, and here as well, okay? So each yi contains only information about one node, while here you have a complicated model which couple everyone, okay? And here you see that you have a kind of function that I call R of t, which defines a signal-to-noise ratio. And this function is whatever we want, okay? For the moment, it's open. The only thing I require is that at 0, it is equal to 0, so I can rewrite it in an integral form like this. Q is nothing else than the derivative of this function. And keep in mind that this function is a free choice, okay? It's whatever I want. So I did that. I defined this extended model. And what I notice is that by construction, the mutual information of this model, okay, if I put t equal to 0, this is nothing else than the mutual information that I want to compute of the SBM, okay? Indeed, at t equal to 0, this object is 0, so these are just pure noisy measurements, so they just go away. And I recover the model that I had. Here, this becomes 1. Okay, it's the model I want to study. While at t equal to 1, this Gij contains no information about the partition, so this is pure noise, this disappears. And I obtain the mutual information for this problem here, which is nothing else, because it is decoupled, n does not appear anymore. This is nothing else than this simple object that appears in this formula, okay? This is just the mutual information of a simple decoupled Gaussian channel. And I just rewrite it here, thanks to this identity, as my potential evaluated in this value minus these terms, okay? This comes from this. I just isolate this term. All right. So this is really by construction. For the moment, I did nothing. So conceptually, what do? We go from a very complicated model associated with a very complicated posterior distribution, and we interpolate, we create a path in time that links this complicated model onto a very simple, fully factorized model where the posterior factorizes, so it's very easy to analyze. Actually, the mutual information associated with this decoupled model is nothing else than this object, okay? And along the way here, which is parameterized by this function that I will call the interpolating function, if you want, I have a mixture model, which is this model, okay, which is complicated, but what is nice is that at least on one side, I have a very simple model, okay? So now, very naturally, what do I want to do? So here I just rewrote the same thing. These are the two boundary values of this object. I just use the fundamental theorem of calculus. My function evaluated at 0 is equal to the one at t equal to 1 minus the integral of the derivative, okay? Trivial. So now the non-trivial part is to evaluate this derivative, okay? But you can do that, and with a bit of work, at the end you obtain a formula that looks like this, okay? I replaced the left-hand side by the mutual information of the SBM. On the right-hand side, I have this part, which is my potential that I want to construct plus stuff. And if I add to these things the integral of this derivative, I obtain these terms that I call remainder in the sense that they remain in between my equality between the mutual information here and the potential. And they look like this, okay? They are both positive. Unfortunately, one of them has a minus, so I don't get directly a bound. I get nothing, a priori. So let's look quickly at this term. We have this first one, which looks like a kind of variance of this q. Again, q is nothing else than the derivative of this function. And there is a second term here that looks as a sum of two squares like this, where this big q, let me call it the overlap, is nothing else than the scalar product between the ground truth partition that I want to reconstruct, and this little x, which is a sample from the posterior distribution, the posterior of this interpolating model, okay? So this little x will always appear in this, inside these brackets, and this bracket notation means an expectation with respect to this interpolation posterior, okay? This posterior that depends on the two types of observations. And I have a second type of expectations here that are expectations with respect to the ground truth partition that I consider as a random object, and the two types of observations, okay? So I have these two remainders. This is just computation, okay? And now, can I obtain bounds, okay? So here I just rewrote the same thing. So let's start with the simple one, the upper bound. So the first thing I do is to take a trivial interpolation path, which means a linear interpolation path. I choose this derivative here to be a constant, but not any constant. I define it to be the argmin of this potential, okay? And if I do that, you see that this term cancels, okay? And what is nice is that this second term, which is positive and has a minus sign, is not problematic to get this upper bound. So I directly get, okay, that this mutual information is less than this function evaluated in Q star, okay? I just look at this sum rule. I replace R1 by its value when I choose that. This becomes Q star. This other term, R2, is positive and has a minus, so I directly obtain this bound. This is the simple bound, okay? Then the other bound, which is, you have to be a bit more careful and smarter, is the most interesting one, actually. So we have to deal with the second term. So R1 is positive again, so it's not a problem because we want to get a lower bound this time, okay? So how do we do? The first thing we notice is that here appears a fluctuation of this object, this overlap, okay, which really physically represents the best scalar product you can aim for between an estimator of the ground truth partition and the partition. And you can prove that this fluctuation here goes to 0 when n gets large, okay? It is a little ON of 1. And this concentration result is what we call in physics replica symmetric behavior. This is why you hear sometime maybe about replica symmetric formula. This is exactly this result, the fact that you can prove that this overlap object concentrates. This is true for any time and almost every value of the signal to noise ratio. This almost every comes from the fact that this is not true, this thing is not small when you are exactly at a phase transition point, okay? But these phase transition points are just lines, they are isolated. So this is why you get this almost every. Okay, so we remove this first term, now we have to deal with this second one. And here, I mean, very naturally, what you want to do, because this object is a free parameter, it's a free function, what you want to do is to equate it with this. But here you have to be very careful. Why? Because this object, okay, I remind you that this bracket means the expectation with respect to the posterior of this interpolating model. This object is itself a function of this interpolating function, of R, okay? And here, this is the derivative of R. So is there a solution? And the answer is yes, because you have a very nice structure that appears, which is a first-order differential equation. You want to equate little q of t, which is free at the moment, with this object in order to cancel this term. But you can do that because this little q is the derivative of this big R, and the dependence of this object is exactly on R of t. So you recognize a first-order ODE, and so you can show that there exists a solution, and thus you choose it, and you cancel this term. So this is why we call this name adaptive interpolation, adaptive in the sense that we adapt this interpolation path to cancel, to obtain the result that we want. And doing that, we obtain the other bound. This term is positive. This is not a problem, and we finish the proof. So just one comment on a technical point. You don't need to parse that. Forget about it. This is not important. What I just want to say is that usually in this kind of techniques, people are trying to map models onto Gaussian models because then you rely a lot on this simple formula, which is the Gaussian integration formula, what we call the Stein's lemma sometimes. But here the point is that we managed to deal with this Bernoulli variable because we used the kind of approximate integration by part formula, which I think is of interest in itself, which we adapted from formulas in Talagrand's book. And that allows us to deal with this kind of Bernoulli variables. But this is much more general, okay? It allows to deal with any kind of random variables. So thanks to that, I mean, you can analyze more model and you remove the need of mapping your model of interest into a Gaussian version. Just one comment about this method. It has also been used to treat some other problems. You can look at this paper if you are interested, which has just been published recently, where we treat the so-called generalized linear model. Example of this GLM are the compressive sensing, this linear regression problem we've heard about, or the phase retrieval problem, or the so-called perceptron, or one-bit compressed sensing problem in the teacher-student scenario, but also the symmetric and non-symmetric tensor factorization problems. So this method is quite versatile. So. Finally, we also managed to extend this method also to sparse problem. One of them is the so-called sensor block model, which is a version of low-density generator matrix. But this is much easier than the real challenge that if you are interested, you can think about that. It's a complicated problem, which is the sparse version of the stochastic block model, okay? In the case where the degree of the nodes remain constant in this limit of large graphs, the mutual information formula is still open. And I will end on just a little advertisement. If you know people or if some of you are interested in this kind of subjects, so I have a 3 years funding for a postdoc in my group in Trieste, in Italy, at ICTP. So you are more than welcome to talk to me. Thank you very much.